In this video, we're going to focus on heat engines. So what exactly is a heat engine? A heat engine is a device that converts heat energy into mechanical energy. Now, heat naturally flows from a high temperature to a cold temperature, and as it flows down, some of that energy can be used to perform mechanical work. So let's work on this problem. We have a heat engine that absorbs 4,500 joules of heat energy from a hot reservoir and discards 2,500 joules into the environment. How much work is performed by this heat engine? So let's draw an energy flow diagram. So this device represents the heat engine, basically this circle in the middle. Now the amount of heat energy that's being absorbed is 4,500 joules. This is the hot reservoir, and this is the cold reservoir. So heat naturally flows from hot to cold. And so this is the engine, the circle in the middle. So 4,500 joules of heat energy is absorbed from the hot reservoir, and 2,500 joules of heat energy is expelled into the environment. How much work is performed by this heat engine? Well, we need to know what the variables are in this problem. QH is the heat energy absorbed by the engine per cycle. So that's positive 4,500 joules. It's positive because the system, the engine, is absorbing heat energy. QC is negative 2,500 joules. It's negative because the system releases heat energy into the environment. And the mechanical work is the sum of these two values. Now, if you're dealing with just positive numbers and you don't want to be bothered with a negative sign, you can also use this equation. It's the absolute value difference of these two numbers. It's QH minus QC if you're just dealing with positive numbers. So that's going to be 4,500 joules minus 2,500 joules. And so that's 2,000 joules. So in this section, that's how much heat energy is being converted to mechanical work. It's 2,000 joules of heat energy. And this makes sense. The engine absorbs a total of 4,500 joules of heat energy. And then it releases 2,500 joules and 2,000 joules. If you add 2,500 and 2,000, that's 4,500 joules. So if 4,500 joules of energy goes into the system, in order for the system to maintain its temperature, it has to release 4,500 joules of energy. So the amount of energy that comes into the engine must equal the total amount of energy that leaves the engine so that it can maintain its original state. Now let's move on to part C. Calculate the thermal efficiency of this engine. The thermal efficiency is the mechanical work divided by QH multiplied by 100%. So in this example, the mechanical work is 2,000 joules. The amount of heat energy that was absorbed by the hot reservoir per cycle is 4,500 joules. And then we need to multiply this by 100%. And so the efficiency in this example is 44.4%. And so that's the answer to this problem. Now let's move on to number 2. A steam engine performs 6,000 joules of work while discarding 14,000 joules into a cold reservoir per cycle. How much heat energy is absorbed by the hot reservoir per cycle? So let's draw a picture. So here we have our energy flow diagram. And so this is going to be the hot reservoir just like before, and this is going to be the cold reservoir. So 6,000 joules of mechanical work is being performed, so that's W. So we have that. And the steam engine discards 14,000 joules into the cold reservoir. So that's the absolute value of QC. QC is negative 14,000. How much heat energy is absorbed by the hot reservoir per cycle? So we're looking for QH. So we know that W is the absolute value of QH minus QC. So QH is going to be W plus the absolute value of QC. And QH is going to be positive. So W in this example is 6,000 joules and QC is 14,000 joules. So QH is going to be 20,000 joules. And so 20,000 joules of thermal energy is taken from the hot reservoir per cycle. Part B. Calculate the thermal efficiency of the steam engine. The thermal efficiency, just like before, it's going to be the work divided by QH times 100%. So the work output is 6,000 joules. QH is 20,000. Let's multiply that by 100. So the efficiency in this example is 30%. So that's the answer for part B. Now let's move on to part C. What is the power rating of this engine in watts and also in horsepower if it takes 0.25 seconds to complete a cycle? So how can we calculate the power? Power is work divided by time. And so we have the work, it's 6,000 joules per cycle. However, we have the time it takes to complete a cycle. Work is in joules and time is in seconds. So 1 joule per second is equal to 1 watt, which is the unit for power. So keep that in mind. Now what I'm going to do is start with this value. The work output is 6,000 joules per cycle. So in 2 cycles, the machine or the engine will do 12,000 joules of work. In 3 cycles, 18,000. In 4 cycles, 24,000. So every cycle that the machine goes through, 6,000 joules of mechanical work will be performed. Now, it takes 0.25 seconds for 1 cycle to be completed. So if we set up this way, notice that the unit cycles will cancel, and this is going to give us the unit joules per second, which is equivalent to a watt. So it's 6,000 joules divided by 0.25 seconds. So the power rating is 24,000 watts. So that's the first answer to part C. Now we also want the power rating in horsepower. And you need to know that 1 horsepower is equivalent to 746 watts. So 24,000 divided by 746. And so this is equal to 32.2 horsepower. So that's the power rating of this particular engine or steam engine. Now, how much mechanical work is performed by this engine in 1 hour? So how can we get that answer? What we need to do is start with the power rating. But first, let me get rid of some stuff. We said that the power rating is 24,000 watts, which is equivalent to 24,000 joules per second. But actually, I'm going to start with hours. So the time is 1 hour. Now we know that power is work divided by time. So if you rearrange the equation, work is power multiplied by time. So I'm going to convert hours into seconds. 1 hour is 60 minutes. And in each minute, there are 60 seconds. So now I have the time in seconds. I'm going to multiply it by the power rating, which is 24,000 watts or 24,000 joules per second. So the unit hours will cancel, the unit minutes will cancel, and also the unit seconds will cancel as well. So this is going to give me the mechanical work performed by this steam engine in 1 hour. So it's 60 times 24,000. So that's going to be a very big number. So it's 86,400,000 joules. Or you can write it as 8.64 times 10 to the 7 joules. So that's how much mechanical work can be performed by this steam engine in just 1 hour. Number 3. A jet engine has a thermal efficiency of 18%. If it performs 1500 joules of mechanical work per cycle, how much heat energy is absorbed from the hot reservoir per cycle? So we need to calculate QH. We have the mechanical work W and the efficiency E. So we need to use this formula. Efficiency is equal to the mechanical work divided by QH multiplied by 100%. So the efficiency is 18%. The mechanical work is 1500 joules. So the first thing we should do is divide both sides by 100%. So 18% divided by 100% is 0.18. And that's equal to 1500 divided by QH. So at this point, we can cross multiply. So this is going to be 1 times 1500, which is 1500. And then that's going to be 0.18 times QH. So to calculate QH, we need to divide both sides by 0.18. So QH in this example is 1500 divided by 0.18, which works out to be 8,333.3 joules. I'm just going to round it to the nearest whole number. And so this is the answer for part A. Now let's move on to the next part. How much heat energy is discarded to the environment per cycle? That was not supposed to happen. So we need to calculate QC. So we know that W is the difference between QH and QC. W, the mechanical work, is 1500. QH is 8,333. And so to calculate QC, what we need to do is basically subtract both sides by 8333. So 1500 minus 8333, that's negative 6,833. So we can see that the absolute value of QC is 6,833 joules. So that's how much heat energy is discarded to the environment. Now, if you want the actual value of QC, keep in mind that it's really negative. Because the heat engine or the jet engine releases that heat, that's an exothermic process. And anytime the system releases heat energy, that process is negative for Q. But if you're not worried about any negative signs, you could say that 6,833 joules of heat energy was discarded. Now, let's move on to part C. How much mechanical work does it perform over 200 cycles? Now, keep in mind that it's 1500 joules of mechanical work per cycle. So all we need to do is take this value and multiply it by 200 cycles. So 1500 times 200, that is equal to 300,000 joules. So that's how much mechanical work the jet engine performs over the course of 200 cycles. And so that's it for this problem. Number 4. A gasoline engine is burning 1.5 kilograms of fuel per hour. The energy of combustion of this fuel is 450,000 joules per gram. If the engine goes through 100 cycles per minute, how much thermal energy is absorbed per cycle? Now, our goal is to calculate the energy per cycle. So we need to perform a unit conversion process, and our goal is to get joules on top and the number of cycles on the bottom. So I'm going to start with the rate at which the fuel is burned. So 1.5 kilograms of fuel is burned per hour. So we need to write it like this. Now the combustion is joules per gram. So that indicates that I need to convert kilograms to grams. So 1 kilogram is equal to 1,000 grams. And so we could cancel the unit kilograms. So now I can use this value to convert to joules. So the energy of combustion is 450,000 joules per gram. Now I still have a unit of time that I have to get rid of. And this value connects cycles with time. So I have 100 cycles per minute, which means I need to convert hours into minutes. So 1 hour is equivalent to 60 minutes. So the last thing I need to do is multiply by the number of cycles per minute. So in 1 minute, there are 100 cycles. So we can cancel these units. So now I have the energy in joules per cycle. So it's going to be 1.5 times 1,000 times 450,000 divided by 60, and then divide that by 100. So this comes out to be 112,500 joules per cycle. Now because the thermal energy is absorbed by the engine, this has to be QH. And so that's it for part A. Now let's move on to part B. If 30,000 joules of mechanical work is performed per cycle, how much heat energy is discarded per cycle? So we know that W is equal to QH minus QC. So our goal is to calculate QC. So let's rearrange the equation. I'm going to take this term and move it to this side, where it's going to become positive QC. And I'm going to take W, move it to that side, where it's going to be negative W. So this is how we can calculate QC. So QH is 112,500 joules per cycle, and the mechanical work is 30,000 joules per cycle. So if we subtract these two numbers, this will give us 82,500 joules. And I need an extra zero. That's supposed to be 30,000 as opposed to 3,000. So this is the answer for part B. Now let's move on to part C. What is the power rating of this engine in kilowatts and horsepower? So how can we get that answer? We know that power is work divided by time. And we have the mechanical work. It's 30,000 joules per cycle. And we have the time it takes to complete one cycle, which is currently 100 cycles per minute. So let's multiply by that. Now we need it in seconds though, because 1 watt is 1 joule per second. So let's convert minutes to seconds. 1 minute is equal to 60 seconds. So it's going to be 30,000 times 100 divided by 60. And so the power is 50,000 watts. Now to convert that to kilowatts, we need to divide it by 1,000. 1 kilowatt is equal to 1,000 watts. And so 50,000 divided by 1,000 will give us a power rating of 50 kilowatts. So that's the first answer to part C. Now let's move on to the second part of part C. So we need to convert watts to horsepower. So let's start with 50,000 watts. And 1 horsepower is 746 watts. So let's take 50,000 and divide it by 746. And so this works out to be 67 horsepower. And so that's it for part C. Now the last thing we need to do is calculate the thermal efficiency of this engine. So the efficiency is going to be W divided by QH multiplied by 100%. So the work is 30,000 joules. We have QH, which is 112,500. And then let's multiply the ratio by 100%. So the efficiency is 26.7%. And so that's it for this problem.